Please, Antoine.
Merci beaucoup Félix pour cette introduction. C'est avec beaucoup de plaisir aujourd'hui que je vais vous présenter mon travail de thèse que j'ai réalisé à RCA donc sur l'analyse micro-inertielle des instabilités dans les milieux granulaires, avec comme application l'analyse de l'érosion interne. Donc, comme a commencé à le faire Félix en introduisant ma présentation, le jury est international, donc je ferai ma présentation en anglais. So the general context of my research lie in the assessment of the mechanical stability of hydraulic structures, such as dikes or dams. Most of the time, these hydraulic structures are built of natural compacted granular materials, and they are thus permeable to internal fluid flows and sometimes subjected to internal erosion. In the worst cases, internal erosion can cause the catastrophic failure of the hydraulic structure. To give a few figures, in France, we count today more than 19,000 kilometers of dikes with an average failure of one dike per year. Among these failures, 45% are attributed to the internal erosion processes. As a result, this generates the following questions, which were at the initial motivation to found my PhD. How does an internal fluid flow affect the mechanical stability of a dike? Will the dike eventually break when it is subjected to internal erosion? Can we know when? How can we build more resilient dikes? And how often should we repair old dikes subjected to internal erosion? Today, nonetheless, I will focus on this only the first question. Following an international workshop in 2005, it is now widely acknowledged that internal erosion can be subdivided into four elementary mechanisms, namely the backward erosion process, the contact erosion process, piping erosion, and suffusion. Suffusion, which is the selective erosion of the finest particle of a soil, is the least understood of these four mechanisms and the only one for which there still exists no practical recommendation to prevent its occurrence. In addition, compared to the three other types of internal erosion, suffusion is specific because it is indeed a material scale issue. Locally, an internal fluid flow modifies the microstructure of a granular material, which in turn changes its constitutive behavior at the material point scale. From an engineering point of view, as taking into account suffusion into the numerical modeling of hydraulic structures has to be done thanks to an evolution of the constitutive parameters of the behavior of the soil at the dike scale. But what are the internal fluid flow effects in terms of microstructure evolution, and how does this affect the mechanical behavior of the soil? These questions are indeed quite difficult to answer to, and this is the reason why historically suffusion was assessed thanks to an internal stability approach. A soil is assessed to be internally stable if it can retain its fine particles inside the material. As a result, most of the existing criteria used to assess the susceptibility of a soil with respect to suffusion are based on geometrical consideration in order to prevent the loss of fine particles. But this criterion dismisses completely the consequences in terms of mechanical behavior. In the lab, suffusion has been widely tested thanks to the use of erodimeter cells, and sometimes these cells coupled with triaxial apparatus. This enabled to test the validity of the different internal stability criteria used found in the literature, and also to start exploring the mechanical consequence of suffusion. More recently, with the increased computational power at our disposal, we found more and more numerical studies aiming at providing some micromechanical basis for this internal stability criterion, and also to start exploring and modeling the suffusion directly at the microscale thanks to fluid grain coupling scheme. However, so far, all these approaches have some limitations, and I'd like to mention a few of them. From the experimental side, it has been reported several times that in the aerodimiter cells, suffusion tends to localize along the boundary of the aerodimiter cell. As a result, what is measured experimentally is not necessarily a material scale issue, but is strongly influenced by the geometry of the aerodimiter cell. Moreover, even if some apparatus exists in the world, it is still very difficult experimentally to impose simultaneously a mechanical stress loading and a hydraulic loading. As a result, there is still few studies that can account for the influence of the stress state on the occurrence of suffusion. On the numerical side, the 3D fully coupled fluid grain coupling problem is still very computationally expensive, and many numerical analysis performed to address the problem of suffusion are tackle this problem either by non-plugging the fluid in and using particle removal processes, imposing a partial fluid grain coupling, or even sometimes by dealing with non-physical 2D problems. In order to avoid producing this same bias, the original line of research I developed in my PhD was to step back and address the more fundamental issue of instability mechanisms in granular materials with an evolving microstructure. In order to address this issue, my methodology was focused on the three following points. First, model the full complexity of the physical process at the representative elementary volume scale in 3D and with the use of a fully coupled and fully resolved fluid grain coupling scheme. Then replace the concept of internal stability by the concept of mechanical stability. And this was achieved thanks to the general criterion of the second-order work group. And then adopt a micromechanical point of view in order to analyze the driving physics of granular materials at the mesoscopic scale and understand what could be the mechanisms responsible for instability linked to suffusion. In the remaining slide of this extended introduction, I'd like to mention the tools and the conceptual framework that backs my PhD. The first tool I want to introduce is the numerical code I use to perform all my numerical experiments. I use Yet software, which is an open source DEM code developed at the 3SL lab in Grenoble. In this code, both the grain-grain interaction is accounted for thanks to the simple elasto-frictional contact law, and the fluid grain coupling scheme thanks to the recently developed 4-scale finite volume scheme, which enabled to account for the fluid grain interaction locally with a fully coupled and fully resolved numerical scheme. And today, it is probably one of the few coupling schemes that enable to tackle 3D problem at the scale of the representative elementary volume. Another thing I'd like to introduce is the concept of four chain, which is, to me, very important to understand the physics and the mechanical response of granular materials. It was initially discovered by, with the use of photoelastic grain, as shown on this picture here. And when a stress state is applied to granular material, the granular materials reorganize to build elongated structures able to transmit stresses through the medium. As a result, a granular material can be seen as a two-phase medium with chain grains that transmit stresses in the medium and non-chain grain that provides lateral support to the elongated structures. In all my PhD work, I used the definition of four chains introduced by Peters et al. In 2005 to define what I call a fourth chain in my medium. This definition is based on three criteria. First, the grain should be heavily stressed, meaning that the principal stress in each grain should be higher than the average stress, principal stress in all the grains. Then the direction of compression should be aligned with the direction of contact between two adjacent chain grains. And then a force chain should be constituted of at least 3 particles in order to generate some internal degrees of freedom and to deal with a real structure. As I started to mention it earlier in my introduction, I wanted to replace the concept widely used of internal stability by the concept of mechanical stability. Because what is really at stake when we consider suffusion in dikes is the creation by the fluid of underlying mechanical instability that will be triggered off later on when the mechanical loading is slightly changed. So the real question at stake to address the consequences of suffusion is what will happen if the mechanical loading is slightly changed? Will our material collapse or not? A proper criterion to answer this question has been introduced in the mid-20th century by Hill and rely on the definition of the second-order work, which is W2 here, and that reads in an incremental formulation as a double dot contraction product between an incremental stress and an incremental strain. An instability definition can be provided as the existence of incremental loading leading to the vanishing of the second-order work criterion. The physical meaning behind this definition can be found by writing the kinetic energy balance equation here. Starting from an equilibrium state, the variation of kinetic energy is the sum of 2 terms, one applied on the external boundary of the solid considered, and one being minus the integral of the second-order work inside the medium. As a result, if this term is negative, it means that provided that this term, we apply an incremental loading such that this term is 0, we have a creation of kinetic energy in the medium without any input energy from the exterior. In this case, our granular material will change from a quasi-static to an inertial behavior. In practice, we assessed the mechanical stability thanks to the use of directional analysis. We apply, for instance, a stress probe, and we recover a strain probe, a strain increment. By combining the two and using here a circular representation in the axisymmetric plane in the stress space, we can get these typical circular envelopes, which is shown here for an unstable material. Because indeed, here, on this region, we have the existence of a cone of instability. We have a set of incremental direction for which the second-order work vanishes. More or less, this cone of instability corresponds here to this physical situation where we impose macroscopically a slight deconfinement of the sample. So in the rest of my presentation, it will be divided into 3 parts, corresponding more or less to 1 year each of my PhD. And first, I want to introduce the definition of mesoscopic scales in granular material. Because if we want to study the suffusion phenomenon at the material point scale, there is a need to define a sample of soil sufficiently big to be representative of the phenomenon. So this will be the first part of my presentation today. Then I will show you some results on the onset, and that will detail the driving mechanisms responsible for instability into dry granular materials. And then I will conclude by showing you some the specific impact of a fluid on the mechanical stability of a granular material. From a conceptual point of view, the whole domain occupied by a granular material can be decomposed into 4 subdomains. On the grain side, we can distinguish between heavily stressed grain and loosely stressed grain by defining chained and unchained grain. And on the fluid side, we can replace the complex geometry of the pore space into 2 pore networks, an accessible pore network and a non-accessible pore networks, with respect to the size of the particles moving through the pore space. These partitions will introduce two elementary scales in between the grain scale and the hydraulic structure scale that I will call mesoscopic scale, and will enable the definition of a representative elementary volume with respect to both stress transmission and transport properties inside the medium. For stress, we can distinguish between chain and unchained grain. And actually, the mesoscopic scale here in between the grain scale and the material point scale is linked to the spatial distribution of force chains. In practice, to quantify this spatial distribution, we can use the 2 points spatial autocorrelation functions. This is this function here, C of h, which is defined as the joint probability that a given point, x, and the translated point, x plus h, simultaneously belongs to the chain particles. If the vector h is 0, here we simply recover the volume fraction of the chain particles in the material. On the contrary, if h tends to infinity, because of the independence of probability, we get the square of this volume fraction. So if we renormalize this function in this form here, we get a function that decreases from 1 to 0 as h goes from 0 to infinity. And the rate of decrease of this function gives us the autocorrelation distance in our material for any direction h. In practice, we have in our material 3 principal directions oriented with the 3 principal axes of the principal stress loading directions. And we estimate numerically these distances by using an exponential fit here, in which we introduce 3 length scale parameters, which constitute my 3 length scale characterizing stress transmission in the granular material. In this slide, I show you the evolution of these 3 length scale for a dense granular material with a quite wide distribution in particle size. And this sample is subjected to a drain triaxial test, meaning that we impose a lateral confining pressure constant, and we impose a vertical strain rate to increase the vertical stress. In this mechanical loading, initially the force chains are oriented quite isotropically, and as soon as we impose the vertical loading, force chains align in the vertical direction of loading and lengthen. And this is exactly what is described here by this evolution of the LZ curve here. What is also interesting to look at on this graph is a Y scale here, which is roughly 4 to 4.5 times the mean particle radius, which is indeed 1 order of magnitude smaller than the size of the sample used in this experiment, which means that we have a sample which is representative with respect to describe the mechanical behavior. For the second property I want to analyze is the grain transport, because an internal fluid flow will make a free particle move inside the medium, and we want to be able to correctly reproduce the transport distances in the medium. If we distinguish based on the coordination number between the geometrically blocked particles in red in this figure and the ratless particle with 0 coordination number in absence of gravity in blue, here we want to have a good idea of how far the blue particle will be traveling to assess the representativeness of our sample to study transport properties. This is done by replacing the complex geometry of the pore space by a mathematical oriented graph. In my PhD, 3 different graphs have been proposed. Either one based on the tessellation of the pore space based on all the particles, including the free particles, and one based on the tessellation of the void based only on the large particle, or well, not on the large particle, but on the particle geometrically blocked. So this defines the geometry of the pore network, and then to get the orientation, we have to define a pressure map on it, and we have 2 ways of defining the pressure map. either by simply linearizing a macroscopic pressure gradient or by taking into account the local pressure fluctuations, and this is done thanks to the application of the pore scale finite volume scheme. The last ingredient to get the oriented mathematical graph is to define a flow intensity a propagation criterion. This is based on the two assumptions here, that a fluid in between two adjacent pores will flow in a circular tube as a positive flow, and that the force acting on a particle traveling inside the pore space will scale as a viscous drag force and proportional to the fluid velocity. As a result, the driving forces that makes particles move inside the pore space should be equal to the particle size times the pressure gradient times the constriction radius at the power 2. So these two last terms constitute what I call a flow intensity in my pore network. A particle in this network will then move according to the path of maximal flow intensity until it gets blocked by two narrow constrictions. This enables to assess the transport properties inside my pore space without running any fully coupled fluid grain simulation. In this slide, here I perform numerical experiments in which a vertical flow is applied to a granular sample, and I compute on the left the mean transport distances for different particle radius here, and with my three pore networks, so these are the black lines, and directly from the numerical simulation you show on the right, you see on the right, this is a blue curve. What is interesting to see here is that our network models provides upper and lower bound for transport inside the granular medium. Indeed, for this pore network, we are defining very large pore, and we are completely dismissing collective motion and in particular collective clogging. As a result, we are overestimating the transport distances. On the contrary, with these two pore networks here, we are defining very small, very narrow pores, and in practice, the particles that are free to move show effective pores larger. So we are we have a lower prediction, lower bound for our transport distances. The last point I'd like to mention on this slide is the slight difference here between the two pore networks constituted based on all particles, and this highlights the fact that local fluid pressure will generate a slightly larger transport in the medium. So this plays in favor of using fully spatially resolved numerical coupling scheme. And the last thing, and the main reason why we have been doing this analysis is the typical length scale associated with grain transport in this sample is 2 times the mean radius, which is again 1 order of magnitude smaller than the size of our sample. So in this case, for this particular particle size distribution, the sample is representative of grain transport. So now I'd like to show you, so that we have defined what is a sample representative to study suffusion, I want to show you some results highlighting the driving mechanisms at the mesoscopic scale responsible for the vanishing of the second-order work criterion. To do that, I will be using this sample here, which is prepared in an unstable mechanical stress state. So as shown here by this the circular diagram of the second-order work criterion. We have some loading here corresponding to the vanishing of the second-order work. In the video here, we highlight the kinetic energy of the different particles while we are applying an incremental loading corresponding to this direction. So we are applying a mechanical loading that generates the vanishing of the second-order work criterion. As a result, here we see that we have a nucleation of an outburst of kinetic energy that rapidly propagates to the whole sample and will generate generalized particles reorganization and macroscopically a transient loss of controllability. If we want to analyze what is going on inside our sample while applying this incremental loading, we can use the force chain definition and define what we call the force chain bending. This is defined here for a group of 3 chain particles by the definition of an angle beta, the angle beta, which is evolving, and if this angle increases, it means that our force chains goes from a geometrical configuration corresponding to the straight line to a bending configuration. On the left here, I show you on the top the evolution of the kinetic energy, the average kinetic energy for all the particles in black, or for only the particles located in a small control volume around the location of the nucleation of the outburst of kinetic energy. On the bottom graph, I show you the mean evolution of the derivative of this angle, so the mean bending rate, either for the whole sample or for the local control volume here. What is shown by the comparison with these 2 graphs is that we have a localized bending which is preceding the loss of controllability and the kinetic outburst of the outburst of kinetic energy. Another micromechanical insight we can get from the definition of force chains is that we can track the number of contacts with respect to time while we are applying this incremental loading. Here, based on the force chain definition, we define 3 populations of contacts. In blue, we have the contacts between non-chain and non-chain particles. In red, the contact between chain and chain particles. And more interesting are the contacts in green, which correspond to the contact between non-chain particles and chain particles. On the left, I show you the evolution of the 3 contact population, either for the whole sample, which is a graph on the top, or for a small control volume around the location of the outburst of kinetic energy, which is materialized here by the 2 vertical black lines. Here what is interesting to see is that the first the number of contact between chain and non-chain particles decreases, which means that we have a local deconfinement of the force chains, followed then by the bending of force chains, and then here the collapse of force chain, and then a final increase in the number of non-chain contact, because here we are considering a loose sample which is getting denser as collapse occurs. Another thing we can do with DEM is to look at microstructure evolution impact on the mechanical stability. This is very easy, for instance, to increase or decrease the number of free particles inside our sample. This is representative with respect to the diffusion mechanisms phenomenon we want to study, to either the massive erosion of the fine particles of the sample or a massive clogging of particles as coming from upstream in the dike body. So here I show you the initial sample I'm considering with the white particles corresponding to 0 coordination number, and on the right you have the sample deprived from Rackless. On the contrary, here I show you this microstructure evolution when we include more free particles with the blue particles on this graph. In terms of mechanical stability, if we perform a directional analysis and we look at the circular diagram of the second-order work here, we see in all cases we still have a vanishing of the second-order work criterion, the second-order work. But so our material is still unstable with or without Rackless. But what is interesting to look at is that the size of the cone of instability vary when we vary the number of free particles. And the more free particle you have in the sample, the more stable it is. This stabilizing role of free particles can be interpreted from macroscopic point of view with the use of the classical paradigm of elastoplasticity. Indeed, rattlers, by getting jammed into as force chains collapse, prevent the development of large incremental plastic strain. This is the first impact on the constitutive behavior of the material played by rattlers. The second impact is a little more subtle and is linked to the fact that the stress state we are considering is not isotropic. So, as shown in the first part of my presentation, we have vertically oriented force chains in the medium, and when collapse occurs, it occurs principally, mainly along the direction of principal compression. So, the difference between the situation with or without rattlers generate a slight change in the direction of the plastic flow, the incremental plastic flow. So these are the two impacts of rattlers on the constitutive behavior of a granular material. To validate these two mechanisms, we can see and fit a non-associated model for plasticity to describe the mechanical response, the incremental mechanical response of our sample. The model is described here and consists basically of the 7 parameters shown in red that should be calibrated. If we calibrate these 7 parameters and we look at the initial sample, we are perfectly able to reproduce the circular envelope obtained numerically by just fitting these 7 parameters. And then, if we use the analysis from the macroscopic point of view, and if we just tune both the 2 parameters that are the plastic strain intensity and the plastic flow direction, then we are able to adapt this model to describe the 2 artificial microstructures with more or with less rattlers, as shown on this graph here. So this validates the particular role played by free particles inside the granular material with respect to mechanical stability. To finish my presentation, I will show you some results obtained on about the specific role played by the fluid with respect to the mechanical stability of granular material. Indeed, the fluid impact on a granular material is twofold. The first impact of a fluid is to make the free particles inside the sample move. This will generate microstructure evolutions simply by the change of location of rattlers in the medium. The second impact of the fluid is to introduce additional forces on the grain constituting the primary skeleton of the granular material, and by forcing stress reorganization in the medium. So I will explore these 2 aspects in this part of my presentation. The first aspect is the simple transport of free particles inside the medium. Here I am considering a widely graded sample with a quite significant fine fraction, and I am considering the 6 simulations consisted of 2 stress states, here shown on the classical drain triaxial loading curve, 2 flow direction, either parallel or perpendicular to the principal stress direction, and 2 flow intensity. Here is the situation of one of these 6 simulations. The 2 samples, the 2 stress states I've been using are not chosen arbitrarily. One is considered to be stable from the mechanical point of view, and one is considered to be unstable thanks to the use of the second-order work criterion. The bottom graph here shows the evolution of the eroded mass with respect to time as the fluid flow is applied. In all the cases, not a lot of mass of the sample is eroded, and roughly 2% in terms of mass of particles are eroded. But this is consistent with the fact that we have not very important transport distance in this medium. But still, we can see the influence of both the stress state and the sense and the direction of the hydraulic loading. We have a larger erosion if we consider flow oriented vertically in the direction of the principal stress state, of the principal stress. And we have a larger erosion if we consider erosion, the fluid flow for an unstable material. This can be interpreted from the use of, again, force chains and at the microscopic scale, because in the medium, force chains are oriented in the direction of compression, which makes it easier for a particle to be transported if the fluid flows along the direction of force chain than perpendicular to the direction of force chain. The second aspect is that when we go from the stress state here, eta equal to 0.7 to 0.9, we are actually decreasing the number of force chains as we are approaching the peak stress here and the softening regime, and we are increasing the number of rattlers in the sample. So it is normal to find that the sample at the stress state eta equal to 0.9 is more sensitive to suffusion. Then what is interesting to look at is the evolution of the mechanical stability of the sample before and after applying the fluid flow, and so before and after suffusion. Here, the black curve corresponds to the situation before the fluid flow is applied, and the two blue curves correspond to the situation where a vertical or horizontal fluid flow is applied. What is interesting to see is that here the fluid has a restabilization effect. And this is actually completely consistent with the particular role played by rattlers I show you in the previous part of my presentation. And here, rattlers are not predominantly eroded from the sample, but mostly clogged inside the sample. The second aspect, the second impact of the fluid I mentioned before starting to present you the results of this part of my presentation, is the direct impact of the fluid forces onto the primary fabric of the granular material. Numerically, we can isolate this effect by considering a sample in which the rattlers have been removed before applying a fluid pressure drop. This is what is done here for two flow directions and for an unstable sample identified with the second-order work criterion. In both cases, here we see that in the end, we observe the collapse of the sample and the fluid flow perturbations. The perturbation introduced by the fluid is able to trigger off the material collapse. This non-sensitivity of the collapse with respect to the fluid flow direction can be analyzed by looking at the distribution of fluid forces at the microscopic scale. This is what is shown on this slide with the probability density functions associated with the three components of the fluid forces. What is interesting to see is that for the transverse direction with respect to the macroscopic direction of the fluid flow, we observe fluctuations of fluid forces that are indeed not negligible compared to the typical size of the fluid forces acting in the macroscopic direction of the fluid flow. As a result, local fluid force fluctuations play an important role in the triggering of the collapse of the sample. This also advocates in favor of the use of fully resolved fluid grain coupling schemes. Before answering to your questions, I'd like to summarize my main contribution to the state of the art and to provide some prospects for future research projects. On the method and tools, I'd like to mention that the different tools, micromechanical tools I've been using are not specific to the study of suffusion, and I've encapsulated all my functions and methods into Python classes, and I will be happy to share this file with you if need be. The other point I'd like to mention on the methodology aspect is that I provide a detailed analysis of the methodology used to assess numerically the mechanical stability of a granular material. Because indeed, what is at stake from a macroscopic point of view is the use of the classical paradigm of continuum mechanics and most of the time quasi-staticity. But locally, granular materials, the behavior of granular materials are inherently dynamics and results of particles reorganizations. So we have to be careful when we want to apply the continuum mechanics tools to the study of the mechanical stability of granular materials. I also highlighted some mechanisms, some driving mechanisms in granular materials at the mesoscopic scale, and I'd like to summarize the main results I obtained. First, I show that the vanishing of the second order work is linked to force-chain deconfinement and force-chain bending. These are the two preceding mechanisms appearing before the failure of the sample. Then I show you that rattlers or free particles in granular materials have a fundamental role to play with respect to the mechanical stability of granular materials. And this is very important with respect to suffusion because then clogging and erosion have antagonist effects on the evolution of the mechanical stability of a granular material. And then the local fluctuations are important and should be accounted in order to see whether a fluid flow is able to trigger up the collapse of a granular material in itself or not. And the last result I'd like to mention, I didn't show anything on this in my presentation, but is the fact that grain detachment is a non-local phenomenon. It means that what I observed numerically is that first we have force chains reorganization. We generate the global creation of rattlers that are then transported within the medium. This is not the action of fluid on a specific particle, and so we cannot use shield-like criterion to study the detachment in the suffusion process. So, for future perspectives, I'd like to mention that the fact that from a numerical point of view, my particle size distribution may appear widely graded, but if we look at them from an experimental point of view, they are not. And actually, we have a huge gap between what is accessible numerically and what is feasible in the lab, and in the future we will have to merge this gap, and this may go, for instance, with the use of widely graded samples as the one shown in this slide, which correspond to the particle size distribution which is used in the lab at IRSTEA in Aix-en-Provence. So here we have too few large particles transmitting stress to be representative of the mechanical behavior, but still we have nice results, and the interpretation of this result looks promising. In my PhD, I didn't compare my numerical experiments to real one, simply because both the time scale and the length scale accessible numerically are not comparable to what is done in the lab. However, there still exist a few experimental studies with a time resolution which is quite similar to what is accessible numerically, and we are currently investigating the possibility to reproduce numerically these results. Probably one of the best main perspective of my work is development of micromechanical models to bridge the gap between the micro and the macroscopic scale. Because indeed the results I show you obtained in my PhD are not really cannot be used directly at the scale of the hydraulic structures, but they can be used to define mesoscopic micromechanical models that capture the physics of granular materials and then upscale thanks to the use of nicely designed micromechanical models. And then the different mechanical tools, micromechanical tools are developed are not specific to the study of suffusion, and they can be easily transposed to analyze all the striking features of granular materials, and one of those that are quite reported several times in the literature is strain localization to granular materials, and this fact that we have a finite length of localization. So this will conclude my presentations, and I thank you all very much for your attention, and I will be happy to answer your questions. Thank you.